And now on the lighter side of things. Scientific notation. Scientific notation is heavily used in science. Good. What is it really good for? Well, it is really good for representing numbers that are incredibly small, such as the weight of an electron. That would be a very small, mass of an electron. That would be a very small mass indeed. Versus the weight of something quite large. Oh, I actually have something even better, like Bill Gates' worth. Now, Bill Gates' worth, I think it's something like this as of today. Right? That's a lot of money. Now, if Bill Gates increased his net worth by another 1,000, it gets hard to write another, it gets hard to represent that number because it's so large. So we introduced the scientific notation. I'm going to start in a place that is very odd. 1. Now, our number system is base 10. Why do we use base 10? Now, you may be asking, what does he mean? Because we start off with ones, right, in school, and then when we master ones, we started counting up by tens, and then when we start mastering tens, we go up to hundreds, and then thousands. So we basically count in these blocks of base 10. And each time you go up, you increase a magnitude of 10. There's 1. There's 10. There's 100. 1,000. 10,000. 100,000. Now, I'm sure you're getting bored, and I'm getting bored of writing down these numbers. But that's 1 million. Now, 1 billion is, well, that's a lot of numbers to write. But I'm going to write in powers of 10. 1 is 10 to the power of 0. 10 is 10 to the power of 1. 100 is 10 to the power, yikes, is 10 to the power of 2. Now, 1,000, that's where we have a break in numbers, is 10 to the power of 3. 10,000 is 10 to the power of 4. 100,000 is 10 to the power of 5. Now, right, we can start off with ones, tens, hundreds. The next signpost of big numbers, well, the first really big signpost of big numbers is this 1,000. And then it's 1 million. And then it's 1 billion. So 10 to the, I'm so sorry, I just realized that I made a mistake here. 1,000 is 10 to the power of 3. So really, this is the scientific notation for all of the numbers. So 10 to the power of 9 represents 1 billion. And that's kind of important. Now, what is 1/10? 1/10 is 1 over 10. 100th means 1 over 100. 1,000 means 1 over 1,000. Can you make a pattern with the exponents, what you think they will be? And sure, 1/10 is 10 to the power of negative 1. 10 to the power of negative 2. 10 to the power of negative 3. So this is scientific notation. This is how we gauge our number system. So for instance, wouldn't it be nice if I was worth this much money? Now looking at this, that means a billion. 4 times a billion is 4 billion. That's what I wish. All right, powers with base 10 are often used to denote very small or very large numbers. It's called scientific notation. So the format for writing a number in scientific notation is as follows. The first digit of the number followed by a decimal point, and then all of the rest of the digits of the number multiplied by the appropriate base. The exponent of this power represents the place value of the first number. Here we have 124. How would I write this in scientific notation? 1.24 times 10 to the power of, well, what is the place value of that first one? It's hundreds, 10 to the power of 2. How do we represent 35,000 in scientific notation? Well, it's 3.5 times 10 to the power of, well, what does this 3 represent? Well, I know that it's 10 thousandths. Well, you could look up at the table above, but 10 thousandths is 10 to the power of 4 because it's one magnitude more than 1,000, right? 1,000 is 10 to the power of 3, 10,000 is 10 to the power of 4. Yikes, the next number is scary. But anyways, it's 9.07 times 10 to the power of, oh wow. I better start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 10 to the power of 11. See, that's a big number. If you had 10 or 9.07 times 10 to the power of $11, you'd be rich. So I'm going to just do that again by counting up by fundamental groups. Thousands, 3, millions, 6, billions, 9, 10, 11. All right, here we are. We're getting into the nitty-gritty here. 0.02. Expressed in scientific notation, our first non-zero number would be 2. So I would write it as 2.0 times, actually, I would probably write it as 2. 2 times 10 to the power of, now this is in hundredths, -2. And if you're maybe wondering why, let's count by decimals. -1 decimal, -2 decimals. To move your decimal place 2 over to the right, it would be 10 to the power of -2. Now, why did I choose to write 2 and not 2.0? Simply because my level of precision was only down to 1 digit, 2. Now, here I have 3 digits of precision. So I'm going to have 7.86 times 10 to the something, right? So how many decimal places would I move it to? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, let's try that again. 3, 6, 7. And since I moved my decimal place over to the right, it has to be negative. Here, there's 4 digits of precision. 3. So that's what my first number is. Now, times 10 to the negative. Whoa. I have to ask myself, how many decimal places to the right must I move here? Do we agree that this is a very small number? And it's a very small number, so I'm expecting my exponent to be negative. I do not want to have a net worth of 3.005 times 10 to the negative something, because that means that I'm worth no money. This is very small. However, it might be, what might have this value? As I said earlier, the mass of an electron. Well, no, mass of an electron is much, much smaller than this. -3, -6, -9, 10, 11, 12. And sometimes these words have meaning. Mega, giga, nano, milli. You'll probably learn this in science, but all of these exponents are used with